Dear friends, welcome to this electrical engineering knowledge sharing channel eng Power System workshop. We are going to discuss a new session 10, where we will discuss about earthing transformer or grounding transformer and its protection requirement. Now, earthing transformer or grounding transformer, generally from the application point of view, we use in the power distribution system, where the power distribution system has a delta connected system. Sometimes in the delta connected system, it needs neutral point. As delta system cannot provide a neutral point, so what we do, we use some other means or other method to create an artificial neutral point, and that neutral point is achieved using a earthing transformer. The purpose of using this earthing transformer for the delta connected system, because as we know that when a delta connected system has a earth fault, there is no path for flowing the earth fault current. If you see the delta connected system, this is a delta connected system. If there is a earth fault in any of the phase, then the earth fault current cannot flow. Then what will happen ultimately? The delta winding, this voltage goes off. So when the due to over voltage, another phase or the same phase, another earth fault can be created, and then this earth fault is converted to phase fault. And due to this continuous persistent over voltage, the equipment may get damaged. So just to avoid this thing, sometimes utility company feel that they need this delta connected system should be grounded by earthing transformer. I did one job about 30 years back, 25 years back, same delta connected system, Bandel Thermal Power Station in West Bengal, India. They have a delta connected 6.6 kV system, which was designed by which was designed by your Kuljian Corporation a long time back. It is a 60 megawatt 5 units power plant. So after 30 years, they found that their various 6.6 kV motors is continuously getting failed due to over voltage. Then they plan to do this earthing arrangement of the delta system, which I carried out the design part. So that's from that experience and through the process, whatever I have learned, we are trying to display it over here. So I have drawn a typical delta connected system. This is a transformer 33 kV by 6.6 kV. This is a star delta transformer. The secondary size is delta, which is a 6.6 kV feeding power to the various motors. Now, due to this delta connected system, if there is an earth fault on the motor or any feeder, then automatically this earth fault will be maintained. First earth fault will be maintained, and then this voltage will be going up. And due to the rising of the voltage, other phase also will be overstressed, and ultimately another earth fault will be created. Then these two earth fault will become a phase fault. Suppose there is one earth fault over here, another earth fault over here, then this is a common, so this will be considered as a phase fault. Then that will be operating, but it will take some time. So to avoid this thing and to give to protect the motor or to provide the motor with earth fault protection, so they planned this delta connected system is grounded through a grounding transformer. That is the background of the utilization of grounding transformer. Now this grounding transformer, when you use in the delta connected system for creation of neutral, this grounding transformer mainly we use a called interconnected or zigzag transformer. This characteristics of this transformer is during normal condition or during healthy condition of the delta connected system, it will not draw any current. Only the magnetizing current it will carry. But during earth fault condition, it will draw the earth fault zero sequence current. It will flow the zero sequence current will flow through the transformer, and then it will give a zero sequence path to the transformer as well as the external earth point. And then accordingly, basis on the earth fault current, we can provide the earth fault protection to the various outgoing feeders, which I have shown in the previous single line diagram. Now, this construction of this transformer is a very special type. In case of zigzag transformer or interconnected transformer, it is a 3 limbs. On the each limb there is a 2 winding. Actually, each phase winding is split into 2 parts, and the 2 parts is connected in such a way that one part flux or one part current will neutralize the other part current of the same phase. So in the normal healthy condition, both the phase there will be no resultant current or resultant flux. But when there is earth fault, immediately the current will be flowing. That means suppose there is I am drawing one winding. Suppose this is a one winding, and this is a one winding, and this is A phase. Suppose this is A phase winding. Suppose this is A2, and this is a A1. This is a one part of the winding, and this is another part. Suppose this is a A2 and this is a A1. The connection in these two parts, it is actually like auto transformer with a two part. It can say in the another way. This is A phase only. Similarly, B phase and C phase. The current in the winding is flowing such a way. If this current is flowing this way, this current will be flowing this way. Or alternative will be, if this current flowing this way, this current will be flowing this way. That is also that in this combination, suppose this is the combination. In that combination, the resultant current in the winding will be 0. Or in this combination, resultant current will be 0. That is the basic idea to make the grounding transformer. So when it is connected, the winding will carry the same current, but the current in the two halves of the winding, this is one half and this is another half, these two half current will be opposite direction, so they will cancel each other. That is the idea. So how we do this thing? This is actually two same winding, two winding, we connect, we split in two part in such a way. One part, suppose this is a one part of the winding, this is a one star winding. Okay, these are the three winding in one part. This is one part, part 1. Part 2 will be just opposite to this. That means this will be a star winding over here. There will be another winding over here. This will be 120 degree. And this will be another winding over here. This is the part 2. These will be two part, and these two part will be connected each other. Then it will give this resultant condition will be 0. So that is how this connection, we have to, before going to protection, we have to show this connection details, how we'll do that. So there is a logic to make how you can make this thing. The logic is like this. Suppose this is a part 1. How this part 2 is coming? Suppose this is a phase. Suppose this is the A phase. This is a phase, this is a B phase, and this is a C phase. And this is the neutral point we have created. The neutral point is grounded. Suppose in this way. Now, to cancel this A phase current, what we have to do? We have to add another winding over here. So that winding will be cancel this winding. How we will do that? Let's say this is a B and this is a C. So if we consider A is a this way, this is a going in this way, we want to make negative A. So negative A will be this way. This is a negative A, right? This is a B is going this way. We have to make a negative B, means negative B is this way. This is a negative B. And this is a C, means negative C will be this way. This is a negative C. So to cancel each other, so that means this is a negative C is this way, this is a negative B, this is negative A. This direction is this way. So this will, if I put over the A winding, this C vector, this negative C vector. So the negative C vector will be like this. This negative C vector, if we add this A phase, this winding A phase and this winding C phase over A, connect with A phase, then this C will be coming over here. That means this C will be cancelled. When I add this one over here, then automatically this C, the flux produced by this C will be cancelled by this, right? Similarly, this B is a positive B. Now the negative, now this is a negative A. If I connect this negative A over here, this winding, if I connect over here negative A, then this A will be cancelled this A. So this A is cancelled. Similarly here, this is a C. Now this C is, if we connect the C vector, this is a B vector, negative B. If we connect over here this negative B, that means this B, negative B, then this B will be cancelled. That means all threes are cancelled by this thing. That means here we have to connect, this will be connecting here, will be connecting here, C, here will be connecting, here is connecting minus A, here will be connecting minus B. Then we can cancel each other. So that is, we can draw here how we are doing this thing. That is, I have shown over here in schematically. Suppose this is a red color, this first winding, these are the three winding. So this three winding is here. These are the three winding. This is a suppose A1, B1 and C1. This is a start point, and this is a A2, B2 and C2, three start point. This point is shorted, grounded. This is the neutral point. Okay. Now here I have another three winding. These are the three winding. Suppose this is a A winding, this is B winding, and this is C winding. This is a A1, it is a B1, and it is C1. This is a A2, this is a B2 and C2. This is connected with a breaker upstream. This is a, now to cancel what we have said, this is a vector. So A2 vector will be connected to C vector, right? C vector. C vector means A2 will be connected when we want to cancel this C value. Then C value is coming, this is A, B, C, this is a B vector. So negative B is this side and negative C is this side. So we will connect C vector over here, right? C vector on this point. So this A2 will go to C vector. So we will connect from here to C1 and then it is a C2. Okay, the C2 is going here. So when we connect this to this, so this current is following, suppose there is earth fault. I am coming to current distribution separately. Then this and this will cancel. Then similarly now B is here. Now this is a B. Now B will be connected to negative A, right? A, this is A, so negative A. So B will take from here, will connect to A, right? And C, where we connected to C? C is connected to negative B. So C will be going from here and will connect to B. If we connect this way, then this is one of the connection arrangement. In that case, these are cancel each other. Another arrangement we can do in different way. Suppose this is A vector. Now here B, this A vector, we can do another way. We can connect on the A vector. This, you see, this is a minus B, right? This is B, this is minus B. If I connect A vector to minus B this way, that means winding will be here. In that case, the A and B will be, this B will be cancelled by this A, and B, on the B will cancel, on the B will, this B, this is a B vector, on the B vector, this is your C vector. So on the B vector will connect C vector like this. This is a C vector, and then on the C vector will connect negative A. So negative A will be here. This way also we can make another connection. In that case also it will cancel each other. This is one of the option. Second option, what we can do, we can connect in this way also. These are the three windings. These are the three windings. Here is the neutral point is shorted, and these are the three windings. Here this is a A1, it is A2, B2 and C2. This A2 will go, this is your A1, B1 and C1. Here this A2 will go to B1, then B2 will go to C1 and C2 will go to A1. In that case also it will be cancel each other. So here just it will be reverse direction, which I have shown over here. This is I have shown, this connection I have shown over here. You see these are the three ABC, this three ABC. This is a small a, B, C. This is a capital A, B, C. Now A2, this A2, when this is A2, when A2 is connected to B1, this A2 is connected to B1, this is a B1, B2 vector, okay? This negative B1, B2 is this way, so I am making parallel to this, so this is B1, B2. Similarly, this is a B1, this B2 is going to C1, C2. C1, C2 is here, the negative C1, C2, so I am making parallel to this, C1, C2. And then this is your C1, C2 negative, the C1, C2 I am connecting this one. This is A1, A2, this way negative A1, A2 I am connecting over here on the C2. This C2 is connected to, this is C2, C2 is going to A1, A2. Then also this is I am getting the, in both combination we can get this type of connection. In this case what is happening, when there is earth fault current is coming over here. Suppose this is a 3I, earth fault current is coming. This will be distributed in three equal parts. I and I, 3I is coming. Now this I is going this way. So it is also carrying I. This is also carrying I. This is also carrying I. Now this is a one A phase. So if you see the direction of the current, here correction is this way. Here current is following the opposite way. So they are cancelling each other flux. Similarly, B phase also cancelling each other, C phase also cancelling each other, which I have shown over here as well. You see this is a 3I current is flowing through the during earthfall. This will happen during earthfall condition. During when there is any earthfall in anywhere, immediately the earthfall current will coming through the ground, and then it will coming over here. 3I will be coming. 3I will be, because both the all windings are equal value.
impedance value all windings are equal, so equally the current will be distributed I. This current is going this way and then it is flowing this way. So when you look into the A phase, this is the A phase, this current is this way, this current is this way, so they are balancing each other. So there is no net flux in the A phase, similarly net flux in the B phase, net flux in the C phase. So what will happen there? So during normal condition it will not draw any current, but during earthfall condition the current I will be flowing, the winding will see the current flowing through the winding, and it will be going to the earthfall point. When this current is going over, it is coming to the delta winding over here, this current is coming over here, this current is coming over here, then the sum current will be again, this is the fault over here, the total current will be coming from here to the earthfall point and it's flowing this way. So this way, this zigzag transformer, we make it this winding. So it is effectively, there are 6 winding, but it is actually connected effectively in such a way, it will be only 3 winding in phase. It's like a auto transformer. And construction point of view, if you see, it is mounted on the same limb in the 2 part. Suppose this is one of the, it is core type transformer, this is one of the limb. So half of this, suppose this winding is connected here. So this is half of the winding is connected over here, and another half of the winding connected this way, and these are shorted. Okay, so this way it is connected. So this is one limb, 2 winding, but it is interlinked. So like auto transformer leg. So this way, this grounding transformer zigzag, it is called zigzag or interconnected transformer is made. Now this zigzag or interconnected transformer, this another way we can do this. Instead of doing this way, we can use another form of transformer. We can use a star delta transformer. So star point, this will be connected to delta system. This is a delta system. Yeah, it is connected to this, and this transformer grounding is a grounded. So in that case, normal condition, this is a neutral voltage. There is no current flow through this. Ultimately, delta system is grounded through this. But when there is earthfall, it will give a earthfall current. But at that time, due to this primary earthfall current, there is no secondary winding. It will be imbalanced. So what do? We put another winding over here. During earthfall current, it is closed delta. This is another winding, but it is not loaded. There is no line taken from this. It is only giving a path. During normal condition, it is not carrying any current. Only during earthfall time, the current will go. When the current will go through the windings, then immediately it will produce a zero sequence current in the delta winding. But in the closed delta, zero sequence current flow in the closed delta. So it will be living within the delta, and that will balance this earthfall current. So this way also we can make a grounding transformer. But most of the cases we use this zigzag type of grounding transformer for most of the purposes. Okay. Now this grounding transformer rating will be different from the normal rating that I discuss afterwards. Now let's start the protection of this grounding transformer. Okay. Now the grounding transformer, when I look into the grounding transformer, that means it has a zigzag transformer or a star delta transformer. So this is, suppose this is my grounding transformer. I am drawing just one equivalent circuit only over here. So this has a 2 winding. Okay, and then this point is a grounded. Suppose this is a grounding point, this is a neutral. Okay, this is a grounded. Now this transformer is connected through a breaker. So this is a switchboard. This is a switchboard. This is a connected over here. Okay. So this is a grounding transformer. Now when you want to discuss about the grounding transformer, this grounding transformer is facilitating to provide a earthfall current to the other feeders. So it is only a media. It is acting as a media, is assisting to provide a earthfall current to the other feeder which is connected to the delta system. So this equipment, when we look into the protection, there are 2 aspects here. One is that this equipment itself, if it is failed, suppose this equipment faulty or there is a failure, then what will happen? Or this breaker is open, then only the grounding is not there. System is running as a delta connected system. My system is not, in that case what had happened? On this system is faulty, at that time if there is a earth fault, then the earth fault protection will not operate. So it will be working as a like normal delta. So first earth fault it will not work. So second earth fault it will convert it as phase fault. But at the same time we do not, when we do the risk assessment, we never consider 2 events or 2 failures at the same time. The time when this grounding transformer failed and at the same time there is a ground fault, we generally do not consider in that way. So if even that is happened, in that case my system can run even without this grounding transformer as a delta system. So when we are looking into the protection of this transformer, there are 2 aspects. One is if this equipment itself has a failure, there is a fault inside this grounding transformer itself, that is called internal fault. For that we have to protect the transformer. And at the same time, we have to look into when there is an outside fault. During that time, this equipment should not open. Or if it is open, or if it is a sense that fault, it can sense the fault, but it should not trip immediately. It should give enough time to trip the other equipment. If that other equipment fail to trip, then only it will open. So that is the second part, because this, when there is any earth fault in the system, in the 6-point delta connected system, any earth fault, because it is coming from delta. This system is coming from delta. If there is any earth fault in the delta, immediately earth fault current will be flowing through this. So this is not the fault of the transformer, this is external fault. For this external fault, suppose this is a motor feeder connected over here. So there is an earth fault in the motor. So if there is earth fault in the motor, earth fault current will go through this transformer and it is flowing this way. In that time, earth fault, this motor should trip on earth fault, not this transformer. But if this motor fail to operate, or this motor protection fail to operate, in that case, what we have to do? We have to disconnect the earth fault path. In that case, we have to trip this grounding transformer, so the earth fault current will not flow. And then the motor will be running as the first earth fault. Then when the second earth fault will come, then only it will trip on the phase fault. By that time, operator will come and look into this, why the grounding transformer has failed or tripped. Then they can make out. That means when we use this grounding transformer, we have to look into the grounding transformer protection from the internal fault as well as backup of the external fault. These two parts we have to look into. So that means when the grounding transformer protection comes into play, grounding transformer protection has a two part. One is an internal protection for internal fault. One is a protection for internal fault. And another is a protection for external fault. These two faults we have to protect this transformer, but external fault protection will be delayed. It will be delayed. We have to give a delay so that we will give a chance to clear the fault for the respective equipment where the fault has taken place. If that is not clear, then this grounding transformer will take care of the fault. Now, as a normal standard practice, this grounding transformer also, it is a oil field transformer. It is located inside a tank with the oil field and the winding which I have shown. This is a 3 wind, actually 6 winding connected in series, effectively 2 winding. On a mechanical side is 2 winding, but electrical actually it is a 3 winding. Make it a equivalent 3 wind to 6 winding, but equivalently make it 3 winding. So this winding with the core and everything is inside a oil field transformer. It's like a oil field transformer, but the rating of the transformer is very less. That we'll calculate afterwards. Now, as it is an oil field transformer, as we have discussed during transformer protection, this oil field transformer has its own various electromechanical devices which can take care of all the minor fault inside the transformer, interturn fault, if inside there is a ground face-to-face fault inside the winding, or there is earth fault in the winding, or there is a other type of insignificant fault take place inside the winding, if some current material inside, if there is a flashover inside the winding. All this thing to take care of all this failure, we have a couple of devices we generally mount on the oil field transformer. One, we have said oil level gauge. Oil level gauge, we have said OLG, oil level gauge, we have put our oil level OLI, oil level indicator. This will monitor the oil level in the tank. Then we have said oil temperature indicator OTI. Then we have said oil temperature indicator, winding temperature indicator. And we have put pressure relief device for the seal type transformer, PRD, pressure relief device. These are the 3 devices, 4 devices, most of the oil field transformer is there. As this transformer is smaller size, it may happen the vendor, the client who is purchasing this transformer, he may not take both the gauges, he may take only one of the gauges. Whatever, he can take oil temperature indicator or winding temperature indicator. So these are the 4 devices. Normally we always purchase the transformer with this device. This device will protect the transformer from the oil leak. If there is a leak in the oil in the tank, from the tank, then the oil, suppose this is the oil level. If there is a leak in the oil, then the level gauge will give an indication, then it can give an alarm or trip, then we can find out the reason. Oil temperature indicator, when the oil temperature goes up, then we know normally oil temperature we allow up to rise 55 degree or 50 degree ambient. Now if the temperature goes above 55 degree rise, that means more than 105 degree, then we allow generally trip the transformer, or 100 degree we give a alarm. When it comes 105 degree we trip. Similarly, winding temperature indicator, winding temperature we allow another 10 degree more. That means 105 plus 10, 115 degree.
So it has a two contact, one is alarm contact and another is trip contact. So we can set the contact in such a way that if the oil temperature comes, winding temperature comes 105 degree, it will give alarm, 110 degree, it will give trip. So this and all this oil and winding temperature will come up when the transformer is getting overloaded, or if there is interturn fault, or there is a phase fault inside the winding. All this will be protected by the oil temperature, winding temperature. Pressure relief device, if there is a sudden short circuit inside the winding, then you know we have said that there is a oil waves produced inside the tank, and this oil wave, this pressure relief device is a bellows with the springs. So when the high oil wave pressure comes on the bellows, then the bellows get compressed, and then immediately PRB device will operate. This PRB device has a nozzle, it will get out the extra pressure by throwing the oil, or if the oil pressure is not very high, then there is a pin, and through that it will be operate, and then the extra gas or whatever is there is get out, and then automatically it will be reset. So these are the automatic device we are installed with the transformer, coming with this transformer. So this can protect most of the internal fault of this size of a small transformer. But if this fault take place, suppose there is a phase fault on the terminals, it is all are inside the transformer. Now transformer has a terminal box, primary terminal box, secondary terminal box. In this earthing transformer, there is a two terminal box. One is a neutral grounding terminal box, another phase side terminal box, ABC. Now if there is a three bushing over here, if there is a phase fault over here, then that will not be sensed by this winding indicator and all these things, because the fault current will be coming. This is a winding, but these are the three. The transformer winding is over here. Okay. Now this is inside a terminal box, and this is inside winding. Now if the fault over here, the fault current will be flowing this way, so it will not see the winding. So in that case, winding temperature may not come off. If there is earthfall on the terminal box, also in that case also earthfall current will be flowing through the local path. So all this thing will not be protected by this thing. So to protect from this type of fault, as well as a backup for the internal fault, we provide this zigzag transformer with a protection devices. For that, what we provide normally, as it is considered as a transformer feeder, this is a transformer, actually one auto transformer you can say, this is a transformer. This feeder we provide for its internal fault. We put a two set of CT, one set CT we put over here with the instantaneous overcurrent and IDM to overcurrent protection. Okay, another set of CT we provide for 51N protection. Okay, in addition to this, we have already shown how these transformers are connected. This is one part, and the second part is over here, and this neutral point is grounded over here. Okay, so in this neutral part, so there is a neutral over here. You can say there is a neutral over here. This is a grounded. So on the neutral also of the transformer, we provide one 51Z relay. Okay. So for internal fault, this 51Z relay will work both for internal as well as external fault. This 51Z is a common, because when there is any fault in the transformer itself, suppose this winding grounded, this is a neutral port. Now if there is a earth fault, and this is connected, this is connected over here, this is connected over C phase, and this is connected over A phase. So if there is an earth fault over here, then how much voltage over there based on this earth fault current will flow through this, it will come and it will flow distributed through this. So this neutral will be always seeing even the earth fault on the outside. In that case also earth fault current will come through the neutral and it will pass. So in either case, whether external earth fault or internal earth fault, the earth fault on the neutral side will be always sensed. So this earth fault will be providing protection for internal plus external both. But these three protection we are providing only for internal protection of the transformer. If this zigzag transformer has a fault inside the transformer, then this three protection will work. This is for the internal fault of this transformer. But how these CTs are connected, there is for the earthing zigzag transformer, this CT is connected in slightly different way. For the phase fault protection, this CT connected in delta, not in ester. This 3 CT, suppose this is a breaker, and this is going to the winding, right? This is going to the transformer winding. This is a winding, and this is a transformer. Now here, this 3 CT for overcurrent protection, we are providing. These CTs are connected in delta, like this way. Why we connect in delta, I will explain to you. And this is the line side is going, okay? These are the 3 CTs are connected for the 50-51. Then here we connect 50 and 51 relay for each phase. Suppose this is one phase, then this is a 50-51 another phase, okay? And then third phase is a 50, 51, another phase 51. We connect this phase and then we short it and it is grounded local. So this way the phase overcurrent relay is connected. Now when we connect in the delta winding, advantage is this: if there is a, we'll come to that point, this is a 3 connection made like this way, and then what do we do over here in this winding itself? When if you see that this delta winding of the CT connection, it is like this. This is one winding, this is one winding, and this is the 3 winding, and this CT is the neutral. This line is coming over here. We are connecting 50, 51 over here. Okay, this is a 50, 51. This is a, then this is a shorted and grounded. This way, this 3 overcurrent, these overcurrent relay are connected. Okay, then why it is connecting in delta? There is another reason. When there is an external arc fault, suppose this is I am showing over here. Suppose there is an arc fault over here. In that case, arc fault current will pass through this. It is external arc fault, not the transformer arc fault. Now we are talking external. Why this CT is connected in delta? I am trying to explain that part. Now suppose there is an external arc fault over here. If there is an external arc fault, then what will happen? Arc fault current will come over here with the neutral is 3 times of current, 3I is coming flowing through here. It will be distributed I in each phase, and this current is flowing through this. So if you see this transformer current flowing through the transformer is I current, each phase, but this is a 0 sequence current. Yeah, this is a 0 sequence current, and all the current is identical. There is no unsymmetrical value of the current. All the 3 currents are identical. So it is but it is a 0 sequence current. When 0 sequence current flow through a transformer winding, then there will be a 0 sequence current will be flowing in the secondary side of this CT. As CT is connected in delta, we always know when CT or any CT or transformer winding connected in delta, 0 sequence current cannot flow in the line. It will be flowing in the closed winding, inside this winding. So the moment these CTs are connected in delta, and at that time if there is any external arc fault, the arc fault current is flowing through these windings, then these will induce a secondary current on the delta winding, and that 0 sequence equivalent current will be flowing in the closed delta. So if I monitor this current will be, this 0 sequence current will be flowing inside the delta winding like this way. So if we can monitor this current by a relay over here, suppose I put a relay, suppose it is a 50G relay I put over here, or 51G relay, arc fault relay if I put over here, then this 0 sequence current when it is flowing through this inside the winding, in the closed winding, this relay will operate. So to detect this external arc fault, we use this delta connected, and here we put in the winding, this delta closed delta, we put a 51 relay. So that is the purpose of this relay. This 51 relay, when this 51 relay operate, it will not trip this, it will wait. It will wait this 50, when this 51 in, this is a 51 in, this is for external fault. It will wait before tripping this breaker. It will wait for some time. Where the fault, suppose this fault is a motor feeder over here. So if there is a fault over here, so this relay will wait to trip this motor feeder. If the motor, suppose this is a time is 0.3 second. Within the 3 seconds, if this motor feeder is not tripping, then only after that, maybe after 6 seconds, 0.6 second, this breaker will be tripped by this 50A relay. So that arc fault current flowing through this will be disconnected. It will be tripped from here, so no arc fault current will flow. Then the motor can operate for another, wait for the second arc fault as a normal delta. So, and then it will be working for that time, for that time period. So this is the purpose of this delta connection. So in this delta connection winding, delta connection with the closed delta connection arrangement, we can detect the external arc fault by this. So this is for external arc fault, and this is now for internal arc fault. What is the arrangement? There are 2 protection for the internal arc fault of this transformer we provide. One is another set of, we said we put a 2 set of CT over here. This is a 1 set of CT. Another set of CT we put is a summation CT. That is a residual connection we make over here. When there is an internal arc fault, suppose this is a 3 phases, we put a 3 CT over here, and this 3 CT we connected in summation form. This is a summation form we are connecting over here. So this is going over here, and then we connect 51N relay over here. So when there is an internal arc fault, then this is a grounded. When suppose there is an arc fault over here, so immediately what will happen? This arc fault, we have shown the distribution. Suppose there is an arc fault over here, in the arc fault.
then the earth fault current will be flowing through this. So this three phase, there will be current imbalance. So imbalance current will be coming over here, and this 51N will protect that thing. So this 51N for the internal earth fault. So this is the 3 set CD we connected in delta. On the delta line side we will put 50 and 51, and 3 CD we connected in summation for the residual connection for detecting earth fault on this 51N. In addition to this, we can provide a CT over here with a 51G. But this will be operating only for the internal earth fault. But this 51G on the neutral will be operating both for internal and external earth fault. So this should be coordinated with 51N. So if this 51N time is 0.3 second, we may operate this relay 51G at 0.6 second. So we have to coordinate this 51G with this or external earth fault. So these are the protection for the internal protection of the transformer, and the external earth fault, as this is for the earth fault protection, external earth fault we provide by the delta winding of the phase CD, where we can connect to detect the earth fault on the external earth fault. And any other earth fault, always the respective feeder will be protecting, the current will be flowing through this. So this is the arrangement we made for the internal and external earth fault protection of the grounding transformer. Okay. So now let's discuss about the capacity calculation of the grounding transformer. Now this grounding transformer will be operating on the system only for a very short time. Normally we have seen that normal within 1 second this fault should be clear for the internal. If there is external earth fault, to clear as a backup, it will not go more than 2 seconds. Within the 2 seconds it will be clear, or you can say maximum 5 seconds. So this grounding transformer, we never consider capacity calculation. In capacity calculation, we never consider the continuous rating. We take a short time rating of the grounding transformer. Now if we see the capacity of the kVA capacity of this transformer, so this grounding transformer, it is connected with the delta winding. Suppose this is a delta winding, yeah, and the grounding transformer is connected over here and is neutrally shorted, yeah. These are the 3 phases shortage. So if you see this grounding transformer per phase voltage, the phase voltage will be how much? If the line voltage between these two is V, then V by √3 into the current is flowing through this I. So into I, this will be 1 per phase power, per phase kVA. As there are 3 phases, so total will be how much? 3 into V by √3 into I. So this is equal to √3 V into I, where V is the line voltage, I is the current through the grounding transformer during earth fault condition. Okay. So this will be the capacity. Now from this capacity, we can now, this is a continuous rating. Now as we said, the grounding transformer ground fault current will not flow more than 5 seconds. So normal practice for grounding transformer, we always consider rating for 30 seconds. This VA rating we require for 30 seconds. Okay, but this is a continuous rating, but we need there only for the 30 seconds. Now as per transformer loading guideline said that if a transformer continuous rating is, suppose continuous rating is K, then for 30 minute short time rating of the transformer will be K by 6. Okay, based on that guideline, as it is only 30 seconds, not 30 minutes, it is 30 seconds only our requirement. 30 minutes rating will be K by 1 by 6 of the continuous rating. We normally consider this 30 second rating is K by 10. So what is the kVA capacity is coming as per this calculation? We take 1/10 of that is a rating for this grounding transformer. Okay. So the grounding transformer rating calculation will be whatever the continuous rating as per the voltage and current calculation is coming, 1/10 of that will be considered as a grounding transformer capacity. Okay, that is the kVA capacity. Now the voltage rating of the grounding transformer or the insulation grade of the transformer to be decided based on the voltage it is getting injected. Suppose this is a delta voltage. So this voltage, suppose this is the delta, line voltage is V. Okay. Now if this grounding transformer is grounded, these are the grounding transformer, it is grounded directly over here without any resistance. So it is always at 0 potential. So this point voltage will be phase voltage, it will be V. But if this grounding transformer is not solidly grounded, if the grounding transformer is grounded through a resistance, suppose to limit the fault current, suppose this way it is grounded, in that case due to fault current flowing through this I, there will be a voltage drop over here. So this winding will not be subjecting to phase voltage, it will be subjecting to maximum voltage drop can take place over is a phase voltage V by root 3. So this term winding will be subjected to actually the line voltage, full voltage it will be injected, it will be subjected. In that case, grounding transformer winding will be insulated for the phase voltage or for the line voltage. But if it is a solidly grounded, then it will be insulated for the phase voltage only. Okay. So this is the insulation grade, and the current rating will be decided based on this voltage. This voltage we have decided based on that current rating, fault current rating, whatever the fault current flowing through the winding, because there is no phase current flowing in the winding, so there is no consideration of phase current. The V into I, what we wrote over the kVA capacity, root 3 into V into I, this I is the earth fault current. Based on the earth fault current, if this is total neutral earth fault current is 3I, phase winding will be carrying the earth fault current only I amount, which we have distributed over here. So this is the 1/3 of the earth fault current that to be considered during this winding calculation of this winding. Okay, so this is the, and 1/10 of that will be the capacity of the earthing transformer. This is about the earthing transformer. So we are now summarizing the total things. For the internal earth fault of the winding grounding transformer, for the phase fault we provide 50 and 51 protection, and for the 50 and 51 for the earth fault protection we provide 51 on the residual connection on the phase side and 51G for the neutral side, and these two are coordinated, and these also coordinate with the external earth fault condition on the feeder. In addition to this, for external earth fault detection, this and the peculiarities of this is that the phase fault set will be connected in delta, not in star, and on that closed delta part we put a 51 end relay for the external earth fault detection, and the phase city 50 and 51 will be connected over here. That is the protection about this, and the capacity calculation of earthing transformer is 1/10 of the kVA capacity of the transformer based on the fault current and the line voltage. This is the capacity, and the winding connection, though it is a 6 coil, but it is effectively as a 3 winding. Each winding or each limb has 2 parts of the coil. The coil is moved into opposite direction, so the current will be cancel each other, and that will be the peculiarities of the grounding transformer. Normal condition it will not draw any current except magnetizing current, but during earth fault condition it will show the low impedance path, and the earth fault current will be flowing through the winding. This is all about the grounding transformer and this protection system. So I am closing today's session over here. Thank you very much for joining with this discussion, and I am hoping this will be continued in the coming days. Thank you very much.